Thanks for that great talk from BJ. Next talk is from Ben Fish.
Great. Hello, I'm Ben Fish at the University of Michigan. And I think that we have been utterly failing to prevent discrimination and injustice when using algorithms. Just failing. I think this statement requires some explanation. Bear with me here. Imagine the worst unfairness or injustice you possibly can. It might look something like this: concentration camps, genocide, slavery. Each of these have been enabled or encouraged by algorithms, including facial recognition, content moderation, and automated translation. And what tools do we have to stop these horrors? There's activism and regulation, which can be very effective. But there's the question of what rules or regulations that we should push for. It often depends in practice on the details of the algorithms themselves, which in turn requires evaluation and modification of those algorithms. So let's look at the state of the art in algorithmic fairness. Here it is. Here's one representative example of a computational fairness definition. It says a classifier is fair when two groups defined by a sensitive feature A get, on average, equal resources outputted by the classifier, conditioned on members of the group having equal qualifications, given, in this case, by this ground truth label Y. Now, the most basic question I think we can ask is, if we impose this constraint, does it prevent discrimination or injustice or any kind of unfairness? Even when that injustice is the worst, most obviously terrible kind of injustice we can think of, I claim that the answer is no. No amount of equalizing resources across the output of a classifier will prevent genocide, even if that classifier was a primary cause. Now, maybe with hindsight, we can measure the effects of the classifier and stop using it, or better yet, stop using an algorithmic approach entirely. But that hardly gives us much warning in advance. And if we can't prevent the most obvious discrimination in the world, what hope do we have? Now, the definition I just showed you is far from the only one that's been proposed in a growing literature. Now, we could ask, what if some other definition, maybe we just chose the wrong one, could prevent an algorithm from promoting discrimination? I think this in turn provokes a question we have to answer. Given a constraint or algorithmic tool of some kind, how do we know if it will prevent harm? Especially given that, quite famously, these definitions are not always achievable simultaneously. We're going to have to choose between them based on the situation or the context we're dealing with. This means, in turn, we have to be able to write down what that context is, which I think in turn provokes another question we're forced into answering. How do we model what's relevant for a particular domain or context? But even if we could do this, I think there's an even more fundamental issue we're going to have to deal with. What does fairness even mean? This equalized odds definition is grounded in what we refer to as distributional equality, where distributional equality means equalizing people's opportunity to get stuff, resources. But as been argued quite a number of times at this point, what if equality of opportunity just isn't sufficient for fairness? If there is an alternative we need to consider, I think we need to be able to express that alternative in terms precise enough for algorithm or mechanism designers to be able to use. This gives us three, to put it mildly, very challenging questions to answer that I don't think we can avoid if we wish to make meaningful progress. Here, I don't pretend to provide answers to these questions, but today I'm just going to try to provide some initial evidence that is at least possible to make progress on these. To do this, let me introduce the very simplest possible system that I can. We are going to use a very simple bargaining model of a hiring market. There are multiple reasons to consider hiring markets, but at least one is that they have long been a place to better understand discrimination. Now, this model is simple. There are just two players, a firm and a candidate. The firm offers a split of a unit surplus, which is just the total benefit the firm and the candidate get by entering into an agreement, by the candidate getting a job with the firm. Now, the offer may depend on the candidate, so I'm going to represent the offer as a classifier F. Now, if the candidate accepts the offer, then they just split the utility that they already agreed on. On the other hand, if the candidate rejects the offer, now the firm has to find a different worker and the candidate has to find a different job. And so they go to the open market and something happens. For the sake of simplicity, I'm just going to say that they're handed some outside options. They find another job. And in these slides, I'm calling it, it's a little hard to see here, but I'm calling that OX and OF. Now let's look at an equilibrium in this game. Here, the firm will offer none of the surplus to the candidate and keeps everything for themselves. Let's say, it doesn't even have to be true, it can be false, but it doesn't have to be true that the candidate believes that if they reject this offer, they will receive the same thing from the open market. They'll get nothing. And so the candidate is indifferent between their two options, might as well accept this offer. And because they accept the offer, they're never going to see what they would have gotten if they had rejected the offer instead. This is, turns out, a self-confirming equilibrium. I won't formally define what a self-confirming equilibrium is, but essentially it's one where each player's beliefs about the other player's strategy need only be correct on the equilibrium path. Now let's look at a second equilibrium, which here I'm calling equilibrium B, which is very similar to this first equilibrium. Now the firm offers instead half of the surplus instead, and the candidate believes that if they reject and interview elsewhere, they will receive that same utility of 1/2. Again, the candidate's indifferent between the two options and accepts this now much higher offer. Both equilibria, A and B, are outcomes, even though neither depended on the true outside options, which none of the players ever actually observed, nor any features of the candidate. All possible candidates could be equally qualified. Yet a candidate stuck at the first equilibrium, despite a much better outcome existing, has no rational way to escape. Why? Because it's an equilibrium. A candidate is trapped in equilibrium A with getting nothing for this job for no good reason. And so to me, it appears blatantly unfair. With this in mind, I think we can begin to answer question number 2. Is there an alternative ethical theory that we could possibly base a constraint on? Here, I'm going to use an ethical theory called relational equality. In particular, the relational equality of the political philosopher Elizabeth Anderson. And Elizabeth Anderson's relational equality is very different than the distributional equalities. It says that the goal of equality is not to ensure that everyone gets what they morally deserve, but rather to create a community in which people stand in relations of equality to others. I think this is very nice, if abstract, but this is where the rubber meets the road. If an ethical theory like this one is to be useful for, say, algorithm designers, then we need In practice, we might have to need something mathematically tractable. Elizabeth Anderson goes on to say that relational equality regards two people as equal, this thing that we want, when each accepts the obligation to justify their actions by principles acceptable to the other. In our very simple case, though, this game, the only outcome is utility. And the only goal is to maximize utility. So the only possible principle that could be acceptable to the players of this game is to maximize the other agent's utility. Here we have a constant sum game, though. So this can't always be done, but at the very least, we can make sure everyone gets positive utility. Now, with our two equilibria I discussed earlier in mind, we can now define the following. I'm going to call an equilibrium to be blatantly unfair to a player X in a two-player game if, one, the payoff for X isn't positive. So think equilibrium A, the first one. But two, there's an alternative equilibrium, think equilibrium B, where both players receive positive payoffs. This is some kind of formalization of relational equality, at least for complete information in two-player games. But with this definition, we can now check if a constraint will prevent unfairness by just checking whether it results in this blatantly unfair equilibrium. Unfortunately, there exists a classifier which can be played by the firm in this game that is at a blatantly unfair equilibrium for every possible candidate, yet satisfies any computational or even economic definition of fairness you can think of, including group fairness definitions like the equalized odds one I had presented at the beginning. Okay, so this is essentially an impossibility result. It says that you can't be both group fair, for example, and not blatantly relationally unfair. Okay, so it's an impossibility result, but if you agree with me that this simple example captures some kind of real discrimination in the world, I think this result is stronger. It says that these computational definitions of fairness fail. They just fail. It also says how the essentially traditional economic explanations of discrimination are at the very least incomplete. So, for example, in so-called statistical discrimination, candidates who aren't hired are less skilled at equilibrium, which in turn serves as firms' justifications for not hiring them. But here in this example, all candidates are equally skilled. They split the same amount of surplus with the firm, no matter who they are. Yet discrimination can still happen, and does. This means that existing computational and economic definitions of fairness are likely doomed to fail. And the reason why is because they only care about distributional equality and only depend on the output of the algorithm and not the surrounding socio-technical system, like a hiring market. Really, I think, though, the problem's even worse because we're only able to go so far if the only visible outcome, as in this game, is utility. We will always end up with some welfare function, and we do so here. But relational equality is just not about utility. It's about the relationships that somehow bind us together. Now, I think it's easy to criticize algorithmic fairness without being constructive. I know I've done it. It's easy to build overly simplistic algorithms or mechanisms and claim with little evidence that they're fair. I know I've done it. But I think it is the defining crucible that will make or break the fields we're all in to find a meaningful alternative. I'm eager, okay, let's be real, I'm desperate for your ideas about how to do this. So please do come find me and chat. I'd like to thank my wonderful co-author, Luke Stark, and thank you all for listening. Any questions?
Hi, thanks for the talk. So in behavioral economics, there is, the inequality aversion. And so basically you're weighing the distance between your payoff and someone else's payoff, right? And so if you add them to these models, I mean, I don't know what the weight is, but you can imagine some sort of weight that comes from like empirical studies of like how much differences between, incomes, costs, any like social cost. I don't know, like that's just something that popped out. Like what would happen?
So when it comes to things like, adding weights to utilities to create some kind of welfare function.
The differences, yeah.
There's, in some ways, this work creates its own welfare function. So we can, for example, judge whether one outcome is preferable to another by, in this case, it's just by checking whether all the utilities are positive. And that's a welfare function of a kind. And so we could change that welfare function by adding weights. The crux of the problem, though, right, is that those weights are not just empirical in the usual sense, right? They're normative. Anytime we change weights of any kind, no matter what the data we got it from, we're claiming that they have kind of a moral significance. And it might be helpful. You might, for example, just axiomatically declare that your system of weights is the right one. And you might be right for all I know. But I think it's incumbent upon us to, one, justify that welfare function through some principled means. And that's one of the things I tried to do here, which is to start with an ethical theory. There's other ways you could do it, of course, but that's the way I chose. And two, I think part of what this work shows is that we really run up against the limitations of what we can do by using welfare functions. If the only thing we have is utility, then there's just not that much we can do. We write down this welfare function, we write down a definition, and what we get out is we have to balance somehow these utilities. And there's often not going to be a great way to do it, I think. And so I want to stress that relational equality in particular is about much more than utility. And to do that, to express that, especially mathematically, we need to be able to express the socio-technical systems that they're part of. And we run into this dead end. Sorry, I'm just ranting at this point. But we run into this dead end where all we have is utility, and it's so seductive because we have these well-defined mathematical outputs, but they don't express the underlying socio-technical system. I don't know if that was an answer to your question, but I hope that was helpful.
Thank you.
Hi. Thank you. That was amazing. Just a little question. So everything you say, great, but the processes before algorithms were part of them were not always completely free of bias and fair and perfect. So do you take that into account in any way, like as a baseline? Are we doing something better or worse than the existing?
Yeah, so this is something I've thought about, I've at least tried to think about quite a bit, because it might be hard to see this from the perspective of this room, but it turns out most of life is not algorithms, right? And most of the socio-technical systems that we embed some kind of algorithm or mechanism mostly consist of not algorithms and not mechanisms. So there's lots of problems here. Like, one of them is that no matter what change to an algorithm you make, it's not necessarily going to fix anything, because often the problem is just not a particularly technical one in the first place. There's many other problems because, right, I think you're pointing out that essentially most of the socio-technical system, most of the interactions between people are invisible to the algorithm. And when those interactions create discrimination in some manner, then of course the algorithm is going to be completely blind to it. And it's so easy, as we've seen, to reproduce that inequality or that discrimination. And that's why I've tried to stress that if an algorithm is going to be useful, if we are going to be able to do anything here, we have to have what I've been calling value legibility. We have to be able to see the moral implications of your given socio-technical system inside the algorithm. And in this talk, I've done a very simplistic job of that. I have one little game, that's my entire socio-technical system. But I'm implying that I think the direction we need to go is therefore modeling much more complicated systems. Again, I don't know if that helped, but.